in this work, we actually want to access the servo loop data directly, so MT Connect is not fast enough to provide that.
So the application he's talking about was actually developed by Accuma for a very specific use case where a person was trying to actually use inspection data to feed back into the machine and actually drive process improvements. I think they were able to get it pretty close to 1,000 hertz, but they did that by essentially shutting everything else down.
Right.
So there was only one data item that was being reported by what is called an adapter, which does the translation.
So what were they measuring?
Position data.
Of the
Position of the tool. So it's the X,
well,
Y, Z.
but not the end effector position of the motors, right?
Well, I mean, I guess yeah. In the end, it is the position of those motors, but it's reflective of the end effector for the tool
If
itself.
there's not too much deflection, right?
Yeah, yeah. I mean, the machine tool is really rigid.
Usage and so on.
Yeah, so the assumption is rigid. Yeah, but you know, to that end, I guess the reality is it's just relative, right? So if you think about, you mentioned force. If you want to do force control in the robot, if your robot's very compliant, then you really, you don't need, sort of the feedback thing, right? So, a little bit of motion gives you a little bit of force, so you're okay. But that little bit of motion with a hybrid, low compliance or high rigidity robot gives you a huge amount of force, so you need a faster loop. So it's relative.
So because everything is so rigid, it becomes essential to go very fast.
Yes, because it's basically a high gain system. Exactly.
So for Roby, he's talking about thousands is what you really want and need, but most of MT Connect applications actually is more for monitoring. It's a lot of sort of steady state type phenomenon. So most adapters may be a hertz, 10 hertz.
Yeah. In fact, actually, this issue about inferring force from power, it turns out power has got a pretty significant lag because you're looking at your motors and blah, 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 blah. So that's about a hertz. And so it just doesn't make any difference whether you get better than a hertz on your feedback because your motors, that signal's going to. I mean, there's lots of interesting things going on in there. So good.
Right. So
we digress.
The point I was trying to make there was that for closed loop position control applications, the currently available feedback methodologies are not sufficient, or at least those on that slide are not sufficient. So anyway, so we talked about the basic building blocks, we talked about feedback, we talked about voxel-based CAM, we talked about a lot of things. So in order to give us a little bit more motivation here, actually I want to point out the performance that we see when executing densely sampled toolpath from a voxel model on a state-of-the-art CNC machine. So this data here was taken from a Mcas smooth 5-axis CNC machine tool. And this actually shows toolpath execution time as a function of programmed feed rate. So for this particular experiment, the toolpath consisted of 10,000 collinear movements of 1/10,000th of an inch each. So the toolpath was 1 inch long, consisted of 10,000 movements. Each one was 0.0001 inch long each. And as we increase the programmed feed rate, we see the actual average feed rate, which is the toolpath execution time divided by the distance traveled, increases in a linear fashion, suggesting that we are able to map the programmed feed rate to the actual feed rate correctly, but then it begins this saturation phenomenon, and this was performed for each axis, X, Y, Z, B, and C. And this is actually a consequence of the online trajectory planning strategy that we talked about, because the look-ahead buffer has a finite depth, and so as we fill up the look-ahead buffer with smaller and smaller moves, the machine must limit its speed so that it doesn't, because it can't see any further past the look-ahead buffer. So actually, just some other data that we see when we do this experiment. If the movement length is 1/1000th of an inch, we have a actual average feed rate, saturation feed rate of 120 inches per minute, and if it's 5/1000ths of an inch, it's actually beyond 150 inches per minute. So the point is here that the movement length does influence the maximum speed that we are allowed to traverse the toolpath. So that is the kind of motion aspects of CNC control and what are the limitations of using G-code for voxel-based models, but also there are a couple other more qualitative things we can talk about here. The first of which is that we cannot specify the positional derivative profile using G-code. So we can only specify the maximum velocity that we are allowed to traverse along a particular movement primitive. We can't specify how fast to accelerate, what jerk to provide, etc. So this has been pointed out by Shu is the bottleneck of high performance machining. Really, G-code in general actually is the bottleneck of high performance machining. And some machines may allow you to modify the acceleration limit through an NC parameter, but we cannot modify any derivatives past that. And we also cannot do that programmatically, so we can't do that within the program as we're running. We also see there's a lack of high density bidirectional data transfer between the CAM system and the CNC. So as we try to provide a high density toolpath to the CNC system, we see velocity saturation. If we want to read data back, high density data back using empty connect or something, we see there are some gaps there in how dense data we can get. There's a cross-compatibility issue when we use G-code. There are machine-specific instructions for different kinds of machines, so we have to have all these different kinds of host processors. And finally, as has been pointed out ad nauseum, the proprietary nature of current machine tool control systems permits limited modification. So this has been known to the research community for a while, and there have been a lot of attempts to address various aspects of these issues. The first and probably most well-known is referred to as StepNC, which was primarily developed to address interoperability between different types of machines and also bidirectional data transfer between CAM, CNC, and between CNCs. This is an object-oriented machine tool programming language where we specify part features instead of absolute movement commands usually. And it allows for interoperability because if we have two different configurations of machines and we ask them both to drill a hole, they may do it in different ways, but we'll still end up with the same hole. So we just say hole here, pocket here. We don't say move Z-axis to this position and then perform peck drilling cycle. A spin-off or kind of offshoot in some extent of this is called NC.js, which is a real-time machining simulator that was actually submitted to the MT Connect Student Challenge a couple years ago and won the first place. Here's a screenshot of that. So this uses MT Connect data to simulate a StepNC machining process. Here is shown a 3-axis vertical machining center, but they're working on 5-axis as well. One of the issues with StepNC, particularly if we want to control motion exactly, is that the movements of the machine are determined by the StepNC interpreter. So we don't, typically, if we're programming feature-based, we don't give exact positions to move each axis to. The machine will decide how to do that, and it will decide how to plan the trajectories to do that. So we don't have exact control over what the machine is going to do necessarily. Also, the data rate available for feedback is limited by the MT Connect adapter, which is specific to the machine tool, and since machines are proprietary, then that would be difficult to change. There have also been a number of interpolation schemes developed. Sai et al. Developed a Pythagorean hodograph interpolator, actually with Faruqi's group, who is big into Pythagorean hodographs, and they showed this on a software platform called OpenCNC, which is a, well, not that OpenCNC actually, because they point out that the implementation of the Pythagorean hodograph interpolator was limited by the openness of the control, ironically enough. But anyway, we also have seen Erkorkmaz and Altintas. I could be butchering the names completely, I'm not sure.
You got Altintas down.
They developed a quintic-spline interpolation strategy using trapezoidal acceleration profiles. So instead of using trapezoidal velocity profiles, they used trapezoidal acceleration profiles and then interpolated position, velocity, and acceleration using quintic-spline segments. And then Cheng et al. Developed a native NURBS interpolator implemented at the Servo loop rate, which remember is the fastest real-time thread that runs in the real-time system. And actually this particular one has gained a lot of traction because a lot of machines now have integrated NURBS interpolators. Some of them may be faked with biarcs, but some of them do have NURBS G codes that we can use. So this did catch on. And you simply provide control points and not vector and weights to define the NURBS curve. These interpolators are great, but they rely on parametric curves, which we don't have from a voxel model inherently. So that kind of limits how useful the interpolators can be in this particular application. And again, they're also limited by the proprietary nature of the machine tool control system. So at last, we get to some prior research works where researchers have developed open architecture, what are called open architecture CNC systems. Minhat demonstrated a StepNC interpreter that was native to the machine tool, so it did not convert StepNC files to G-code and then run them. It actually interpreted them directly and used enhanced machine controller which again, we will talk about that in a moment. That is in this project. It used the enhanced machine controller to machine 2.5 axis parts, which means that X and Y move simultaneously in Z steps. And then, I don't know how to pronounce this one, so I'll say Baudet et al. Created what they call premium open CNC, which is shown in this image here, to perform direct trajectory interpolation on the surface. So this, they provided the CAM surface directly to the machine instead of using kind of chordal approximations along the surface to show performance improvements over the Siemens 840D, which is widely regarded as the gold standard CNC controller. So these open architecture systems, actually, we didn't see much direct integration of the CAM system. They're still reading, maybe this one is reading in a parametric surface for the premium open CNC. In Minhat, we're reading in a step NC file. So in order to address more of these deficiencies, actually this proposal proposes the use of what we call direct servo control and analysis from the CAM system itself. So to reiterate, the main issue is that there is an insufficient data pathway between the CAM system and the CNC. Again, proprietary architecture of the industrial CNCs doesn't allow us to change them, so we need to look at something else. And previous approaches to enhanced control of the machine may not address the entire problem. Some don't allow us to control every aspect of machine motion, as is the case in the step NC example. Some do not integrate the CAM system completely, so we still have some middleman between the machine and the CAM system. Some don't provide dense in-process feedback for us to analyze the toolpath offline. And finally, there are kind of disparate methods